So let's take a look at this week's homework and run through some of the answers. Question 1 was a little bit counterintuitive in its wording, but let's take it from the point of view that most people took it and list these 4 groups from the highest priority down to the lowest. So as we look at the first carbon in the chain for each of these 4 groups, the highest priority atom we can reach for these 3 are a carbon for the first one, a carbon for the second, but this third chain here, we can look down to the bottom of the molecule and straight to a nitrogen, higher atomic number than a carbon. So it actually makes this one the winner and the highest priority chain straight away. Going on to the second carbon in the chain for the other 3, we can look at the next 3 atoms in line for these 3 chains, and for the first one we have a choice of nitrogen, carbon or hydrogen. So let's list those choices from highest to lowest priority. For the second chain we can go to a chlorine, carbon and hydrogen, and for the last one we have a carbon and we have a nitrogen double bond. So we treat that double bond as if it was 2 individual bonds to 2 individual nitrogens. So nitrogen, nitrogen, carbon is the choice for the last chain. So comparing highest priority to highest priority, the chlorine wins for that second chain, so second highest in priority, and then for the first and the fourth chain, nitrogen to nitrogen, so it's a tie. Then looking at the next best choice, carbon to nitrogen, because of that double bond to the carbon, that gives us third place, and therefore fourth place to that last chain. Comparing atomic numbers for atoms at the comparable positions in each chain. Now we've got a mechanism for a halohydrin reaction. Okay. So to start our mechanism off, we have the alkene acting as a nucleophile and using the pair of electrons from that double bond, we have spontaneous polarization of the electrons in the bromine to bromine bond. We cause a new carbon to bromine bond and break up the bromine, and we get a carbocation intermediate, which follows Markovnikov's rule to add the bromine to the side with more hydrogen, and we get the more stable carbocation, a tertiary carbocation rather than a secondary carbocation. Now, because of the close proximity of the bromine, which is electron enriched, it can use its pair of electrons to form a bromine to carbon bond and form a bromonium ion bridge. We know the true intermediate structure has resonance like this because some of the character of the final product can be explained by the bromonium ion bridge. With the cycle in the molecule, the second addition across the double bond is trans to the first. Because of that big fat bromine, it prevents attack from above, and the secondary nucleophile has to come in from below instead. But our first resonance picture shows us the carbocation nature of that apex carbon in the right hand corner. So when the competing nucleophile comes in, water, which is a stronger nucleophile than bromide, using a pair of electrons, it attacks at that carbon with carbocation nature, and it causes the carbon to bromine bond to break. Always think about this domino effect of new chemical bonds forming and old chemical bonds breaking. Remember, we say that these two structures are resonant structures to each other. Both of them are showing character of the true intermediate. Some of you, for your answers in the homework, you are showing these half-headed arrows. Remember, these are equilibrium arrows, and we're saying that the molecule is flipping back and forth between the two states. Here, it isn't a rapid flip, it's just that the true nature of the molecule partly looks like this and partly looks like this. We have resonance. So water in the second step, that fast step, is the beta nucleophile in the second step. The carbon to bromine bond breaks and the electrons go back to the bromine. So we get this oxonium ion formed. For a positive charge on the oxygen atom, some people's answers left a second lone pair of electrons on the oxygen at this point. Remember, that would put 10 electrons in the oxygen's outer shell. It cannot happen. So then a second molecule of water, this time water acting as a base instead of a nucleophile, using a pair of electrons to pick up a proton, and the electrons go back to the oxygen. So we get a final product, the halohydrogen with an alcohol group and a halide on opposite sides of the plane of the ring. Be careful where you're drawing these electron arrows. They're showing where the electrons come from, and they're showing us where the electrons go to when new chemical bonds form or old chemical bonds break. Second one on page 2, done much better. We have an alkene reacting with a hydrogen halide compound, the hydrogen bromide. And as we've seen before, there's a polar covalent bond in the hydrogen halide molecule. The alkene acting like the nucleophile, picking up a hydrogen, causing the hydrogen to bromine bond to break, and we form a secondary carbocation. Now, the secondary carbocation is preferential to this position because it gives us neighbouring alkyl branches. So it gives us the possibility for a 1-2 shift of one of those methyl groups. Remember, be careful where the arrow comes from. It's not coming from the carbon at the end or the carbon at the centre. It's the electrons in the bond which are hopping across and taking that relatively small methyl group with it. We've got sp2 hybridization here with an empty atomic orbital above and below the plane. And overlapping in close proximity is the carbon to carbon bond with those bonding electrons. So the 1-2 shift occurs and it moves the positive charge across. Now this is the atom with an incomplete octet and gives us the more stable tertiary carbocation instead of a secondary carbocation. Anytime the molecule is capable of forming a more stable carbocation, we will see this 1-2 shift. So now in the much faster second step, that bromide acting as the nucleophile to our electrophile carbocation, forming a new chemical bond and producing our haloalkane product. The energy diagram showing the energy of the initial reagents, the alkene, and the energy of the final product. We have a energy of activation for that first step, and then the energy of activation for the second step. A much smaller energy of activation second time round because of the faster more favourable exergonic step. The energy of the intermediate is in between the two, and a reaction